In this video, we will look at the concept of viscosity. When two solid surfaces are in contact, we split the forces between the two surfaces into their components. Specifically, we look at the perpendicular component and the parallel component. So for example, supposing we had two solids A and B meeting at some surface, and let's say that A is moving with respect to B, so we have a velocity of A with respect to B, it's moving to the right like this. Then there will be a force of B on A, and let's say in this example that it points in this direction. So what we do is split it into a component which is perpendicular to the surface where they are in contact, right? So perpendicular to this surface, and a component which is parallel to the surface. The perpendicular component is what we call the normal force, and the parallel component is what we call the frictional force. In this case, because there actually is motion, it would be kinetic friction between A and B. So this is the normal force of B on A, pointing up like this, and this is the frictional force of B on A. Right, and together combined, they make this contact force of B on A. Now, of course, if we looked at B's free body diagram, there would correspondingly be a normal force of A on B and a frictional force of A on B pointing in opposite directions, normal force downward and frictional force to the right. But for now, we'll focus just on how we can split this force into a perpendicular component and a parallel component. Now, the reason why we had two different objects meeting at a surface is because for a perfectly rigid object, which is the type of object we've been looking at so far, the internal forces and the internal arrangement of molecules is highly constrained. So for a perfectly rigid body, the distances between the atoms are fixed. The body as a whole may move or rotate, but there is no motion between the layers of atoms inside the body. Right? So the center of mass can move, and you can have rotation about any axis that you like, but the distances between various atoms stay fixed. However, in all other cases, that is, gases, liquids, non-rigid solids, atoms can move relative to each other. And we see this in the form of the fact that fluids flow, fluids here including both liquids and gases, and solids can deform. If we look at solids and look at the forces between layers of atoms, again we can split up those forces into components. So the force which is perpendicular to the layer of atoms is equal to the normal stress times the area. Right? So normal stress is sort of like pressure, right? It has units of newtons per meter squared. So you multiply the stress by the area to get the force, and it is perpendicular to the layer of atoms. However, we can now also have a force which is parallel to the layers, right, which is trying to make one layer slip past another, attempting to at least, and so that is equal to the shear stress times the area. Notice it's shear with an EA. Now in liquids, we will have a fairly similar scenario. So in liquids, when they are flowing, there is a situation called laminar flow. And in such a case, the liquid's molecules will follow smooth streamlines. That is, they follow smooth flow lines, right? They move in nice smooth lines, and you don't really see much mixing between the layers of liquid. These smooth streamlines or flow lines do not cross, and they behave like very smooth lines, and so you don't see eddies or turbulent swirls, so there's not really much mixing action. Right? So if you released a little bit of ink into the fluid, it would flow in a nice smooth line. So again, now that we have laminar flow, so there are fairly well-defined layers of atoms in the liquid, we can talk about the force perpendicular to the layer per unit area. So the force per unit area perpendicular to the layer is called pressure. All right, so if you want the force, you would do pressure times the area, would give you the force perpendicular to the layer. All right, so pressure is equal to F perpendicular over A. But you can also have force parallel to the layer between the layers of liquid, and this is the viscous force. So basically it is like friction, one layer of atoms trying to stop a neighboring layer of atoms from slipping. Right? It's trying to prevent motion between the layers parallel to the surface of contact between the layers. And this is called the viscous force. So the systematic way of thinking about the viscous force was actually first systematized by Newton. And so here's a rough schematic of the idea he had. So imagine you have a large metal plate. Here we're showing it in cross section. So you have one large metal plate here, you have some liquid, and then you have another large metal plate on top. And what you do is you give the top plate some velocity v. Right, so the plates are separated by a distance delta y, which is entirely filled with liquid, and I'm here just representing 3 layers of liquid. Right, so you can think of these as being the molecules of the liquid, if you like. And this is the y direction, this is the x direction. So the bottom plate is stationary, and the top plate is given some velocity, and it's made to move with some nice constant velocity. So what do we think will happen to the liquid? Well, we imagine that the layer of liquid which is right next to this bottom plate would stay stationary. And this layer of liquid which is right next to the top plate would acquire pretty much the same velocity. Right? So the top layer will have velocity, the bottom layer will be stationary, and in between we expect there will be a sort of linear progression here. There will be some in between medium velocity for the middle layer. And this makes sense because as this layer is moving, so why is this layer moving? There are forces between the plate and this top layer of the liquid. So as the plate moves, those forces attract the liquid and move it also. And then this tries to attract the next layer, so it tries to get it moving, but it has a resistance to moving, so it only acquires some velocity. And then you can see there's a gradient going on here, and the velocity decreases and eventually reaches 0 at this layer, which doesn't really want to move anyhow because it's next to this stationary plate. So notice that what we have is a velocity gradient. Right? Velocity changes in space. As we move position, the velocity changes. Now, it's important to remember that these forces between the layers of liquid and also between the plates and the liquid, all these forces obey Newton's third law. So just like there is a force that the plate exerts on this top layer, trying to pull it to the right, there is a force that this top layer exerts on the plate, which is trying to stop it from moving, well, which is trying to pull it to the left instead. And just like this top layer is trying to pull this middle layer to the right, the middle layer is trying to pull this top layer to the left, and so on. So the force required to keep this plate moving at a constant velocity tells us something. It is basically the viscous force. So this F parallel, right, it's parallel to these layers of liquid. We expect it to be proportional to the area, because the more the plate is in contact with the liquid, the easier it is for the liquid to exert this retarding force on the plate which is moving. So it's proportional to the area. And we expect that this force is also proportional to the velocity gradient, right? So how much does the velocity in the x direction change as you move in the y direction, right? How steep is this gradient? How steep is this change? Will be proportional to the force. If you want this plate to be moving very fast, then you will need a larger force, right? And the steeper this gradient, the more quickly velocities change from one layer to another, again, the greater the force required. And so this was a proportionality, and so now we turn it into an equality by filling in this unknown constant, and this is the viscosity. to make it somewhat comparable to pressure, we often divide over the area, and so we say the shear stress, which remember is, it might have the same units as pressure, but it is not a pressure, because pressure is perpendicular to the layer. Shear stress is parallel to the layer. The shear stress is the parallel component of the force divided by the area, and that is equal to eta, which is the coefficient of viscosity, times the velocity gradient, dv over dy. Yeah, so yes, these are the various quantities. Eta is the coefficient of viscosity. In the units of eta, we can see if we solve for eta, we would have F over A, so newtons per meter squared, and then we divide over the velocity gradient. So the velocity gradient is meters per second over meters, so we divide that over, so we have meters on top, meters per second in the denominator, and we simplify and we get it to pascals times seconds. So that is the SI unit for the coefficient of viscosity. So it's not unitless, right? The coefficient of viscosity, which depends on the liquid and also on the temperature at which you measure it and other quantities. The units of eta are Pascal seconds. And sometimes you will see the unit poise. Poise is the CGS unit for the coefficient of viscosity. So 1 Pascal second is equal to 10 poise. In the next video, we will take this understanding of viscosity and actually apply it to an example and see how that shapes the velocity profile of a river.